This one is C5H12O. It has 0 double bond equivalents. We have a 1H broad, that's going to be an OH. We have a CH2 here, and we have a 6H, which is going to be 2 CH3s, and another 3H, that's going to be another CH3. So we're looking at 1 CH2, and we're looking at 3 CH3s. When we look at what's left over, you can see we've got a carbon atom, and that doesn't have any hydrogens on it, so that would be that one there. Let's talk for a minute about why I chose 6H here to be 2 CH3s and not 3 CH2s. When you're looking at situations where you have a 6H peak, when there's a single peak, a double peak, or a triple peak, due to symmetry, it turns out that those are going to be situations where you have two CH3 groups, generally speaking. The only time when you have 3 CH2s most often is when you've got 4 peaks under the 6H over here. You should stop the video and take a read of this. It's fairly interesting. It gives you some really good background as to why these peaks will usually go for 2 CH3 groups and this one goes for 3 CH2 groups. So we should have the right pieces now, and we can put it together. Now the C is going to go down here, and it's going to have 2 CH3 groups attached to it. That will allow us to explain this 6H peak that only has a single peak. What that means is these CH3 groups must be next to something that doesn't have any hydrogens on it, and in this instance that means this C group here. Notice that they're the same, related by symmetry, and that's why they're under the same peak. We have a CH3 group here that's got 3 peaks, so it must be next to a CH2, and the CH2 must be next to a CH3 because it's got 4 peaks. That leaves only one place to put the OH, and that would be over here. Now I want you to notice that the one thing we could not do is this kind of thing, because the 3 CH3 groups would all be the same, and that would be a single 9H peak. So what we're left with is going to be this situation to explain the structure.